We've talked about how we calculate the size of an electric field, and now we're going to talk about how to sketch electric fields and show not only its size but also its direction. So an electric field is a vector quantity. It has a magnitude and direction. If we start off with a positive charge sitting in space somewhere, and we put another positive charged object here, which direction would it go? It would be repelled from it, it would be going directly that way. Same as if we placed a positive charge there, it would be heading straight away. And no matter where we put that positive charge, it will be always heading away from that central positive charge that's setting up the field. So I'm just going to draw what the field looks like over all space. Okay, so there's our lines which show which way a positive test charge would go, and that is actually the definition of the direction of an electric field. It's the direction that a positive test charge would move. I'll just write that down here. It's the direction a positive test charge would feel a force. I'm going to do the same thing for a negative charge setting up a field. And of course, in this example, if you have a positive test charge sitting out somewhere in space over here, it would be attracted to that negative charge. And again, over here, it will be attracted to that negative charge. And so on, with all our field lines pointing inwards, going all the way to the center with that field there. I'm just trying to make these evenly spaced because it would be evenly spaced for a spherical charge or a point charge. And as has popped up down here, it's the density of the field lines which indicates the strength of the field. So if you look over here at this positive charge here, right close into the positive charge, the lines are very close together, so it has quite a high density of lines, which means the field is very large in the center. As we move out further from that charge, the lines are further apart and the field is weaker. So an object which was out there would feel a smaller force per unit charge than something close in. Again here, and I apologize, these lines really should all come into the center here, that close in, we've got quite a high density of field lines, and out here it's lower, so that field strength is lower. So just a question to consolidate that. Which of these diagrams here represents a field that is created by the largest negative charge? Well, we know that if it's a negative charge, that those lines will be pointing inwards because a positive test charge would be attracted to that charge. If it's a large charge, it means that the field lines are quite close together. And you'll find with this one here, they're all pointing inwards and they're quite close together compared to, say, this one or this one up here. So the answer to the first one would be D. For the second one, which has the largest positive charge, it would be the same situation as for the largest negative charge, so there'd be quite densely packed field lines, but they would be pointing outwards. And so of course our answer is A in this case. For the smallest negative charge, again we've got an attraction, so it should be pointing towards the charge, because if it's a positive test charge it will be attracted to it. And these, in this one in diagram C here, are the most widely spaced field lines, and so that would give us indicate that this was the smallest negative charge. And a similar argument, E would give us the smallest positive charge. We've talked mostly about single isolated charges and what would happen to something in the vicinity of that charge, and we call those monopoles. So these are monopoles. They are just charges in space, and we assume that they're the only thing setting up that field. So of course, for the negative sphere of charge, a positive test charge will be attracted to that negative sphere, so our field lines are going inwards, and conversely, for the positive sphere of charge, the positive test charge would be heading out the way, so our electric field lines point outwards. again, two monopoles. What happens if these two charges are near each other? Well, they would create something called a dipole. And so what would happen here is we would consider what would a positive charge do. If it started off, say, here, it would be repelled away from this positive side, this positive part of the dipole, until it got closer to the negative, and it would start heading back down there. So essentially what we're doing is we're adding the electric field to find out what would happen to a positive charge. If a positive test charge started off over here, it would just zip off into space in this direction, and it would always be repelled more by the positive part of the dipole than it would be attracted by the negative part. So both of them are acting in space all around it, but depending on where you are, you'll be influenced by one more than the other. So one last example here, we've got two charges, 2Q, positive 2Q here, and negative Q here. And at what point is the electric field strength the greatest? So we need to consider the effect of both of those charges on each of these points in space to see at which point the electric field strength adds up the most. So what we'll do is to first consider 2Q. For a positive test charge at point C, it would be repelled from this positive 2Q charge. And so would at D, it would also be repelled. It would feel a lower force per unit charge because it's further away, but it would still be repelled. Again, for B, it's being pushed in this direction, experiences a force that direction, so the electric field strength is pointing in that direction. And again, for A, which is much further away, the electric field strength is very small. Let's consider now the field due to this negative Q charge here. And you can see at point B, a positive test charge would be attracted to that negative Q, and so it would be in this direction, same electric field direction as for the positive 2Q, so those two would add together. At point A, it would also be attracted back to the point Q, to that negative Q charge, so these would cancel each other out somewhat. For point C, a very small attraction because it's further away, so the electric field strength is small. And for point D, also a small electric field strength. So you can see that at point B, it has the largest electric field strength because due to both of those charges, it adds up to, they both add up at point B. They don't cancel each other out as they do at all these other points, and they're both actually quite large. So now on to some more examples with electric fields.